Welcome to an introduction to the chain rule for functions of several variables. We're going to go ahead and start by taking a look at the chain rule as we knew it in single variable calculus. So in single variable calculus, we use the chain rule to find the derivative of functions that were composite functions. For when we had a function g of x, that was the argument or inserted into another function, f of x. And so when we did that, we took the derivative of that outer function and we left that inner function alone. So we took the derivative of the outside function, leaving the inside function alone. And then we multiplied by the derivative of that inside function. Okay, so just a really quick example here. Let's go ahead and find the derivative of f of x equal to 2 to the quantity x squared plus 1. So if I were to think of this function as a composite function, what I see is I have an exponential function. I've got 2 to a power. So this outer function I would consider being 2 to the x. And then what is in that exponent? What is in the exponent for that exponential function? That would be this g of x. And that would be x squared plus 1. So we can check, and what we'll notice is that if I do f of g of x, that's going to be 2 raised to a power, and that power is going to be this g of x function. Now that g of x function is x squared plus 1. So we're satisfied that we've decomposed this function f of x into its two components, the exponential function 2 to the x, and then the exponent where we have x squared plus 1. So now let's go ahead and take the derivative. So f prime of x is going to be the derivative of 2 to the x. So the derivative of 2 to the x is the natural log of 2 times 2 to our power. Now remember, we keep that inner part alone. We keep the g of x. So the natural log of 2 times 2 to whatever power we had x squared plus 1. And then we multiply by the derivative of that power. So in this case, the derivative is 2x. So our derivative will look something like this. So now let's take a look at what the chain rule looks like, or how we approach the chain rule when we have a function of two variables. So here we have a statement of the chain rule in the case where we have one independent variable. So we're supposing that x is a function g of t, y is a function h of t, and both of those are differentiable functions of t. We're also going to suppose that we have a function z equal to f of x and y, and that this function f is differentiable for x and y. So that means that our function z, which is f of x and y, can really be thought of as f of g of t, h of t, because of how x and y are defined. So to find the derivative of z with respect to t, we take the partial derivative of f with respect to x, and then the derivative of x with respect to t. So we're first going to find how this function f changes with respect to x, and then we have to recognize that we also need to consider how this function x changes with respect to t. So we're saying in this formula here, we want the rate of change of f with respect to x and multiply that by the rate of change of x with respect to t. And notice we do the same thing for y. And because both x and y change with respect to t. Now, we can visualize this as well. So let's look at creating a tree structure to help us understand this rate of change of z with respect to t. So in this tree, we're going to capture the rates of change of f with respect to x and with respect to y. And we're also going to capture the rate of change of x with respect to t and y with respect to t. So if I start with the original function, z is a function of x and y, well then there's really two partial derivatives or two rates of change I could consider. I could consider taking the partial derivative with respect to x. I could also consider taking the partial derivative with respect to y. Now, having done those partial derivatives, I've taken care of that outside part of the chain rule. And I'm now to the point where I have to deal with, okay, well, how does x behave? What's the rate of change for x? And also, how does y behave? What's that rate of change for y? So to do that, I need to apply the derivative to both of those functions. Now, when I do that, then I get to the point, so we would need a dx dt. And now I'm finally down to where I understand how the function behaves with respect to t, at least on the x side. Now I need to do the same thing on the y side, so I need a dy dt. So that's the rate of change with respect to y. And at this point, I am now at the t level. I've captured all of those rates of change. So now I'm ready to write my derivative, and I use each branch of this tree to help me write that derivative. So my derivative of z with respect to t, coming down this left-hand branch, first we take the partial of f with respect to z, and then we multiply that by, continuing down our branch, dx dt. Plus, and now I go down my right-hand branch, so I need to apply the partial with respect to y to the function f, so we have partial of f with respect to y, times, and then continuing down that branch, we need to know how y changes with respect to t, so dy dt. So this is a visual tool that you could use to help you remember how to apply the chain rule to a function of two or more variables when you're interested in the derivative with respect to a single variable. In this case, our single variable was simply t. So let's look at a really quick example. What we want to do is find dz dt for our function z equal to cosine of x plus sine of y, where x of t is 2t cubed and y of t is t squared. So my dz dt is going to be the rate of change for my function f with respect to x times dx dt, how x changes with respect to t, plus the rate of change for f respect to y, so how does y change, rate of change for y, times dy dt. Now, that f that we're talking about is this cosine of x plus sine of y. So basically we need 4 different derivatives here. We need the partial of f with respect to x. So that's going to be the partial of cosine of x, so that's negative sine of x. And then taking the partial derivative to sine of y, that's 0. We need the partial of f with respect to y. This time the partial derivative with respect to y is 0 for the first term, and for our second term we get cosine of y. Now we also need the derivative of x with respect to t and y with respect to t. So dx dt is 6t squared, and dy dt is 2t. Now we're ready to assemble all that information here. So dz dt equals partial of f with respect to x, so negative sine of x, times dx dt, so that's 6t squared, plus partial of f with respect to y, that's cosine of y, times dy dt, so that's 2t. And now I do need to substitute in f for x and y. I need to insert this information about x and y into my derivative. So my dz dt is equal to, and I'm actually going to write for my first term, I'm going to write the 6t squared first, sine of x. X was 2t cubed, plus, and then I'm going to write my 2t first, cosine of y, and y was t squared. So there's our dz dt. Now let's take a look at what would happen if our x and our y depended on two variables, u and v, instead of a single variable. Now we have similar conditions. We need the functions g and h to be differentiable for u and v. We also need our function f to be differentiable in terms of x and y. And then we have these partial derivatives for z, because z is actually ends up, because it's a function of x and y, in the long run, it actually is a function of u and v. So z is now a function of two variables, meaning it has two partial derivatives. And so the structure of these partial derivatives is very similar to what we saw when x and y depended on a single variable. The significant difference is that there are now two of them, one for each of those two variables, and instead of having a dx dt or a dy dt, now I have to have partial derivatives for x and y. Now I can do a tree similar to what we did before. So if I start with a function z, a function of x and y, I can do two partial derivatives, one for x and one for y. But then I arrive at these points. I arrive at the fact that I have x as a function of u and v, and I have y as a function of u and v. So now I have to attend to what happens to x and to y. Now, since x is a function of two variables, it has two partial derivatives. It has a partial of x with respect to u, and it has a partial of y with respect to v. Now, at the end, then I've done a partial derivative with respect to u, and there are no additional partial derivatives to take. Similarly here, when I do my partial of x with respect to v, I'm at the variable v, there are no more partial derivatives to take. I can do similarly over here with y. I'd have a partial of y with respect to u, and at that point I'm at the variable u and there's no more derivatives to take. And I can do a partial of y with respect to v. And now I'm at v and there are no more partial derivatives to take. So notice though, I have two possible endpoints down here. I can have a rate of change with respect to u, and there'd be two paths to consider. and I can have a rate of change with respect to v, and there are two paths to consider. So I'm just going to do one of the two paths. So we could start with z, and we could come down this path. So we can have the partial of z of f with respect to x. And if I continue along this path, then I have the times the partial of x with respect to u. And now because I've taken a path that leads to u, this is going to be the partial derivative of z with respect to u. Plus, and now I need to attend to the other path that leads to u. And that would be the partial of f with respect to y times the partial of y with respect to u. And so that's the formula that we have here. So let's look at a quick example. We want to find the partial of z with respect to u and the partial of z with respect to v. So we have the two formulas here that we need to use. And here are our functions. So what we need to do is basically find the partial derivatives for all of these functions. So the partial of f with respect to x is going to be 2x times y. The partial of f with respect to y is going to be x squared times 1. The partial of x with respect to u is going to be e to the 2u plus 3v. And then using the chain rule, the partial of my exponent with respect to u is 2. Then I have my partial of x with respect to v. Again, that's going to be e to the 2u plus 3v. And then taking the partial of my exponent with respect to v, I get 3. For y, the partial of y with respect to u, I get e to the 3u minus 2 times the partial derivative with respect to u in my exponent. That's going to be 3. And I just noticed there's a little typo here. There should be a v there. Partial of y with respect to v should be e to the 3u minus 2v. And then the partial derivative in my exponent should be, with respect to v, is negative 2. Okay, so now we can assemble these into our partial derivative of z with respect to u. So the partial of z with respect to u is partial of f with respect to x, so that's 2xy, times x with respect to u, that's 2e to the 2u plus 3v, plus partial of f with respect to x, that's x squared, times the partial of y with respect to u, that's 3e to the 3u minus 2v. And then we do need to substitute in x and y. So partial of z with respect to u is 2x, that's e to the 2u plus 3v, times y, that's e to the 3u minus 2v, times 2e to the 2u plus 3v, plus x squared, that's e to the 2u plus 3v squared, times 3e to the 3u minus 2v. Now, we can do some algebra to simplify that, but I'm not going to take the time to do that at this point. That's sufficient to show that you know how to apply the chain rule. So let's take a look at our other partial derivative here. I notice I had a typo here. So if you copied down this formula earlier, please correct it. Okay, so what do we have here? We have the partial of z with respect to v. It's partial of f with respect to x, so 2xy, times the partial of x with respect to v. That's going to be 3e to the 2u plus 3v, plus the partial of f with respect to y, that's an x squared, plus the partial of y with respect to v. So negative 2e to the 3u minus 2v. And now we substitute in for our x and y. And so once we substitute in x and y into what we had before, we have our partial derivative of z with respect to v. And again, it's possible to clean that up with some algebra, but this is sufficient to illustrate that you understand the chain rule when x and y depend on two independent variables. I hope you find this helpful.